Hello and welcome to a final exam review video. Okay, this is being recorded in May of 2025. So it's end of spring semester 2025. I'll be looking at the most recent final exam from fall of 2024. Okay, just to give everyone an idea of the kinds of questions that are being asked on a typical Calc 2 final exam. So let's get into it. We're going to go through a series of problems. I will be trying to break up the video into several parts so that the video doesn't get too long. So you may see a few parts coming along in the next few days. Alright, so let's start with the first one. It says evaluate the following integral. It looks like it is a U-Substitution. Okay, so these kind of integrals you want to look at, just take a moment to see what's going on. You have secant squared and tangent, and you'll recognize that secant squared is the derivative of tangent. So what you could do is make a U-substitution with tangent being the u. So we can say u is tangent of x. Du would be our secant squared x dx. Okay, so what does that mean for us? Well, if we integrate and we have secant squared tan x, you can just rearrange and say this is tan x secant squared x dx. And so now when you do your u substitution, you have your u du. And so when we go to integrate this, we'll have u, this is just power rule, so u squared, and then that would be multiplied by 1/2. Okay, we substitute back in, so we'll have 1/2 u is tangent, so tangent squared x, and use our limits of integration. Okay, so what does this mean? It means we can plug in for our pi over 4 for x. Okay, so this is what we'll do. We'll say 1/2 since it's going to be multiplied by 1/2 both times, I'll just pull that out aside. And tangent squared of x is the same as tangent of x squared. So we will say this is tangent of pi over 4 squared minus tangent of 0. So think back to pre-calc when you're doing tangent of pi over 4. Pi over 4 is 45 degrees. So if you have your right triangle at 45 degrees, you'll have something like this. And remember, your 45 degree is going to be part of a 45, 45, 90, where your legs are 1 and your hypotenuse is √2. So tangent opposite over adjacent. So 1 over 1 is 1. And then minus tangent of 0. And tangent of 0 is 0. And so we just end up with an answer of 1/2. Alright, so that is our first problem. Let's take a look at our second problem. Okay, so here we're integrating. It's an indefinite integral of 2 over x squared minus 1. So to help us with this kind of resembles the old integration by integration, and we're going to be doing this with a partial fractions model. Okay, so in order to do that, we would factor the denominator. Okay, so this will look like integral of 2 over, and x squared minus 1 is a difference of squares. So x plus 1, x minus 1. Okay, so when we go to integrate this, we'll know that we can set up the integral, split up two fractions, in this case, one for each of these factors in the denominator. So we would make this maybe, let's say, a over x plus 1 plus, and then b over x minus 1. And so now goes the idea of what do we have to multiply this first fraction by in order to add these two fractions together, essentially. Right? We're not going to really do that, but that's the procedure. Right? So common denominator is x plus 1, x minus 1. So for the case of the x plus 1 denominator, multiply by x minus 1. Right, that's the thing that's missing. And then we'll do that, top and bottom. You're not going to really multiply for the bottom per se, but just as a formality. And then for our second fraction, that one's missing the x plus 1. Okay, so, and now we're going to really focus in on the top portion here, the numerators, right? A is going to distribute, B is going to distribute. We know that this numerator has to equal the original numerator in the problem. Okay, so let's set that up then. So we know if we distribute, we have A x minus A plus bx plus b. And we know that this will equal 2. Okay, so separate out your x's. You know that you have ax plus bx. Right? And then in our original numerator, there are no x terms. So we know that we have ax plus bx, and that would equal 0x. Or in this case, just 0. And then for our constants, we have a negative a plus b, and then we do have constants, we have a 2. So negative a plus b equals 2. Okay, so from this, we're going to come up with two equations. Right, we'll have one equation for the x's, right? Ax plus bx equals 0. So x, I'll say x to the first. So that equation would look like a plus b equals 0. And then the constants, we'll say x to the 0. That equation is already set. Negative a plus b equals 2. Okay, and so now we could easily just solve this little system of equations. If we just add straight down, there's our elimination. A plus negative a is gone. B plus b is 2b. And then 0 plus 2 is 2. So 2b equals 2. divide by 2, so b equals 1. And now going back into either of the two equations, if b equals 1, then we know that a would have to equal -1 for this to be 0. So a equals -1. Okay. So now looking at our integral that we set up here. So a is -1, b is 1. So now let's just plug it in. So a is -1 over x plus 1. And then b is 1 over x minus 1. And now when we integrate, we see that these are both very basic integrals, right? These are both ln's. Okay, so we would have here negative ln of x plus 1 plus, and this one's an ln of x minus 1. And then, because it's indefinite integral, don't forget about the plus c. Okay, very nice. Okay, let's take a look at our next problem. Use the shell method to find the volume of the solid generated by revolving the region bounded by the curves y equals 2 over x, y equals 2, and x equals 2 about the y-axis. Okay, so shell method. Okay, remember just a second what shell method is. To get our volume, we integrate from a to b of 2 pi times the radius, right, whatever will give us the radius, times the height this will be all respect to x. What's interesting to remember here is that when you're revolving the region about the y-axis or about some kind of vertical line, the setup has to be in terms of x's, right? X limits of integration, functions are all in terms of x. Okay, so very important there. Okay, as opposed to disk method, right? Disk or washer. Remember, when you integrate and something is revolving about the x-axis, that's when everything is based on x's. Here it's in reverse almost, right? If you're revolving something about a y-axis, everything is in terms of x's. Okay, and then it would be vice versa for shell. If you're doing about the x-axis, then everything has to be based off of the y variable. Okay, so let's take a look then. Very important to get an idea of what's happening in terms of a picture of some sort. Okay, so if you were to somehow graph this, and it's a very easy graph to make, 2 over x, you can easily just plug in a few values and you'll get an approximate what the graph would look like. You can start with x equals 2 and y equals 2, so you know that x equals 2 is your vertical line, y equals 2 is your horizontal line, and then when you have the curve y equals 2 over x, now you have, well, a couple of the points you have. For example, when x is 2, 2 over 2 is 1. So you'll have this point here. And then when x is 1, you'll have 2 over 1, which is 2. And then you'll have a vertical asymptote at 0, right? So you'll have one of these curves where it's going to kind of shoot up. Okay, so this will kind of look like this. It'll eventually just keep getting, it'll rise and get closer and closer to, as you get closer and closer to 0 for the x, the y would just increase like that. Okay, so the region that we're talking about is this region. Right, this is the region that we're going to be revolving about the y-axis. Okay, so everything is in terms of x. Now, a couple things are going on. This particular shape, when we're talking about the height, that's where we're going to really get stuck. The height isn't the same throughout the whole process here, right? So we're going to be spinning this shape, and the height here is fixed at 2, but in this portion it's changing, right? It's changing throughout. So we could do this in 2 partitions. We're going to do, right, one partition we're going to do from 0 to 1, right? That's all steady. And then the second partition we'll do from 1 to 2. Okay, so let's do the setup then. So we'll have volume equal, and we'll do from 1 to 2. I'll do that one first, 1 to 2. So that'll be from 1 to 2. I have my 2 pi. X is my radius, right? So spinning about the y-axis, so that's going to still be x. And then my height will be based off of the function 2 over x. And so we have dx. Okay. Then in our second integral, we'll do from 0 to 1, 2 pi x, and then the height there is a constant 2. Okay, so, and that'll take care of that portion from 0 to 1. Okay, so let's go through and simplify this. I have x and x cancel, right? So I'll have 2 times 2 pi. So that's going to be integral of 4 pi and again this is from 1 to 2. That's just going to be a constant, so integrating that is very easy. We'll just say that's going to turn into 4 pi x. Okay, and then when we evaluate that, plug in the 2, right? Plug in 2, plug in 1. 2 minus 1 is 1. So we get 4 pi from that part of it. All right, the second part, we have our 2 pi x times 2. So 2 times 2 pi is 4 pi. So we have integral 0 to 1 of 4 pi x dx. Okay, integrating that, now the x will turn into x squared, divided by 2. Simplify that, so now you have 4 divided by 2 is 2, so 2 pi x squared. And that we will say is just going to be evaluating the limits of integration. 0 to 1. Okay, so plug in the 1. Which just gives us 1. So 2 pi Okay, so we have 2 pi from that portion plus the 4 pi from the first portion. So we end up with a total volume there of 6 pi. Okay, let's take a look at this next one. It says find the length of the curve So it's going to be an arc length problem. So in order to do the arc length problem, we have to remember the formula for figuring out the arc length. So we say L equals integral from A to B of the square root of 1 plus the derivative function squared dx. Okay, so in this problem, let's get the derivative function going. So for our purposes, we know we're going to be multiplying the 3/2 times the 1/3. X squared plus 2. Subtract 1 from your exponent. So 3/2 minus 1 is 1/2. And then remember chain rule. That's probably the biggest mistake people make. That's probably they forget about the chain rule. So derivative of the inside, derivative of x squared is 2x, derivative of the constant is 0. Okay, simplifying, 3's would cancel, so we have 1/2 x squared plus 2 to the 1/2 times 2x. The 1/2 and the 2, they will cancel. So we'll just be left with x, we could bring that in front. And then this quantity to the 1/2, we just rewrite it as a square root of x squared plus 2. So that's our derivative. Next, we started there, right? And now we're going to do is square it. So we're going to take our derivative, and now let's square it. Okay, so the x squared will turn to x squared, and then squaring this quantity will come out. It'll no longer have a square root, but we could write it like this, x squared plus 2 with parentheses. You can go ahead and distribute the x squared. So we have x to the 4th plus 2x squared. Okay. So that will go into our formula. Okay, we'll have our integral is going from 0 to 3. So 0 to 3 square root of 1 plus x to the 4th plus 2x squared dx. Okay, upon careful inspection, we could see that we can rewrite this just rearrange it. You'll have x to the fourth plus 2x squared plus 1. Okay, and this should remind us of the old x squared plus 1 perfect square, right? That quantity perfect square. Right, it'll kind of look like if we had, just think about it, x squared plus 1 times x squared plus 1. What do we have? Right, we have x to the fourth plus x squared plus another x squared, so plus 2x squared plus 1. Okay. And a lot of these will turn out to be some kind of, I should say usually, right? Usually it'll turn out to be some kind of expression that you could easily collapse with the square root being there. And it turns out to something you can easily integrate after that. Okay, so this is really the square root of x squared plus 1 quantity squared. And so now when we take a square root, right, the square root will cancel with the square and just leaves us with x squared plus 1. Okay, so that leaves us with the x squared plus 1. And now we could just easily integrate here. We have x cubed. So we'll have x cubed over 3, or 1/3 x cubed. Integrating the 1, we get x. And now we'll plug in 3 and the 0. Okay, so plugging in the 3, we'll have 1/3 3 cubed plus 3, and then minus 1/3 0 cubed plus 0. Okay, well the 0 cubed is 0 times 1/3 is 0 plus 0, so that's gone. And then 3 cubed is 27. And 1/3 of 27 is 9. And then 9 plus 3 is 12. Okay, so that's going to be it for our first part. Like I said, I want to try to split up the review into a few different videos. Hope to see you guys soon, and we'll check you out on the next video.